Alright, here we are to finish up the Chapter 6 material, talking about enthalpy again. Here we're talking about enthalpy of reactions and how we calculate those values. When we want to calculate the enthalpy for a particular reaction, there's no way that chemists are expected to look in a table for that particular reaction and to measure every possible reaction to get their enthalpy. And so there's a way that we've standardized enthalpy calculations, and that's by using the enthalpy of formation. The enthalpy of formation is defined as the energy that's either absorbed or released when 1 mole of a particular substance is formed. Okay, so for example, if we wanted to make a simple compound like sulfur hexafluoride, for example, well, I know that I'm going to make 1 mole of sulfur hexafluoride, SF6. That's going to come from sulfur, which is a solid, and from fluorine, which is diatomic and a gas. This is a gas, by the way. And I got to balance it. Let's see, I need 3 F2s to give me 6 fluorines and 1 sulfur. That's balanced, right? And so by definition, the enthalpy of this reaction, the delta H of this reaction, is the delta H of formation. Almost always, that delta H of formation is calculated at a standard pressure of 1 atmosphere. And so we put a little naught, we say, 0 up there. This is called a naught symbol. And what it means is that it's at a standard pressure. Okay. And so this is what we call the standard enthalpy of formation. Okay. Again, that's the change in heat, the change in energy that results when a single mole of a compound is formed from its elements at a pressure of 1 atmosphere. And so, in order to make this SF6, we have to start with our elements, and they have to be in their standard state. What does standard state mean? Well, it means that for sulfur it's got to be a solid, for fluorine it's got to be a gas, and it has to be diatomic. We could not write 6F here because that's not how sulfur exists in its standard state. When we write these delta HF reactions, these formation reactions, this is where we have to use fractional coefficients occasionally. And so, for example, if I want to make water, well, it's got to be some hydrogen, which is a gas, a diatomic gas, some oxygen, which is a diatomic gas, and we're going to make H2O, which in its standard state is a liquid. If we were to balance this, usually what we would do is we'd put a 2 in front of the hydrogen and a 2 in front of the water and say that that's balanced. We can't do that because our definition tells us that we're making 1 mole. And so we can't have a coefficient of 2 here in front of water. Instead, what we have to do is put a coefficient of 1/2 in front of the oxygen. Okay? So keep an eye out for that. Don't let that trick you up. The definition of delta HF is 1 mole of product. Okay? All right. Once we have these values for delta HF, those are the values that are put into tables, the energy that it takes to make a single mole of a particular compound. Those tables look something like this. This is from our textbook. But you can see that for these compounds here are their enthalpies of formation. Most of them are negative because usually when we form bonds, energy is released rather than needing energy. Another thing that I really want to point out is that for elements that are by themselves, you'll notice that they all have delta H of formation of 0. Because if I'm going to form silver as a solid from its element in its standard state, well, silver in its standard state is a solid. If there's no change between beginning and ending, then delta H must be 0. Sorry, that's running in the table there. But delta H must be 0. And so the delta H of formation for all elements, as long as they're in their standard state, is 0. Right? And we see that all over the place. Here's mercury and iodine. Here's nitrogen, oxygen, sulfur, zinc. Every element in its standard state is going to have a delta HF of 0. Okay? And so how do we use this? How do we put this together? To calculate the enthalpy of a particular reaction, we're going to write it this way. As delta H for a reaction, almost always we run these under standard conditions, and so we put the little naught up there. Okay. And so this delta H reaction, how do we calculate it? Let's assume that we have a reaction that takes A moles of A and B moles of B to give us C moles of C and D moles of D. Right, so of our generic reaction. In order to find delta H for this reaction, we have to take all the energy that's given off or absorbed by the products and subtract all the energy that was given off or absorbed by the reactants. And so that looks something like this. Well, generally speaking, that would be delta H of formation for the products minus delta H formation for the reactants. Right? How do we figure out we've got 2 products and 2 reactants? What do we do? Let me write it out a bit more explicitly. For our products, it's going to be the number of moles of my compound, and so for C, our first product, we have C moles of that, times delta H of formation for compound C. And we're going to add the total enthalpy from D, which is the moles of D, times the enthalpy of formation for compound D. Right? All of that is my products. And then I'm going to subtract an analogous bit for the reactants, and that's A moles times the delta H of formation for compound A plus B moles times the delta H of formation for compound B. And all of that is for the reactants. So products minus reactants to figure out what the overall reaction enthalpy is. Again, these delta HF values that we have for A, B, C, and D, all these come from a table unless it's an element in its standard state, and then it's, did you say 0? I sure hope so. Okay. And so let's do a quick example here. We have a reaction of thermite that involves aluminum and iron 3 oxide. We have 2 moles of aluminum solid plus a mole of iron 3 oxide solid go to 1 mole of aluminum oxide solid and 2 moles of iron as a liquid. And so if we are going to calculate delta H for this, then we need to pull some values from our table. If we go back, I'm just going to go back real quick. Aluminum oxide here negative 1669.8. Iron didn't make it on this list, but I have those. But this is how we use these kind of tables, right? We look up the compound we're interested in, and we jot down the enthalpy of formation for that compound. And so, let's go back here. Our delta H for the reaction is going to look like, well, for our products, we have 1 mole of aluminum oxide, and we just saw that that was negative 1,669.8 kilojoules per mole. And then we have to add to that, we have 2 moles of iron as a liquid. Now, iron in its standard state has a delta H of formation of 0. Is liquid the standard state for iron? It's not. And so it's not 0 here. We've got to look it up. It turns out that it's positive 12.4 kilojoules per mole. So there's my products. Now I have to subtract my reactants. 2 moles of aluminum times now aluminum as a solid. Is that the standard state for aluminum? It sure is. And so that's 0 kilojoules per mole. In reality, when you work out these problems, if you want to omit the ones that are in their standard state, that's fine. I'm just going through it so that you see the process. And then we have 1 mole of iron 3 oxide, which wasn't on our table, but in the back of our textbook, that's negative 822.2 kilojoules per mole. Okay? And so we do products minus reactants. And so we get a delta H of reaction of negative 822.8 kilojoules. Now notice all of our moles canceled. And so we're just left with kilojoules. If it asked for the delta H of reaction, then we would be done. But it doesn't. It asks us how much heat is released in kilojoules per gram of aluminum that reacts. So we don't need kilojoules. We need kilojoules per grams of aluminum. So let's take this one step further. We have negative 822.8 kilojoules. And in our reaction, let me go back. In our reaction, we had 2 moles of aluminum. And so that kilojoules is divided by 2 moles of aluminum. Right? We get out 822.8 kilojoules of energy for every 2 moles of aluminum that react. It doesn't ask for kilojoules per mole. Again, it asks for kilojoules per gram. But 1 mole of aluminum from the periodic table, 26.98 grams of aluminum. Our moles of aluminum cancel, and we're left with 15.3 kilojoules per gram of aluminum. Okay? And so we use those delta H of formation for all the compounds that are in that reaction. We do products minus reactants, making sure to account for the number of moles in the balanced chemical equation. Once we find that, that's delta H reaction. If that's what the question asks for, we're all set. If not, we've got to take it a step further to go to kilojoules per mole of a particular compound or kilojoules per gram of a particular compound. Okay. All right. The last part of chapter 6 that we're going to talk about is Hess's law. And Hess's law tells us that we can sort of pick and choose the reactions that we're interested in order to come up with a particular value that we're missing. Let me show you what we mean. In this reaction here, let's say that we don't know this enthalpy of reaction. Right? We know the enthalpy of reaction going from carbon and oxygen to making CO and an oxygen atom. And we know the enthalpy to go from carbon monoxide and oxygen to CO2, but we don't know the enthalpy to go from carbon and oxygen all the way to CO2 in one stretch. What we can do, Hess's law tells us that we can mix and match equations in order to figure out an overall reaction. And so from carbon and oxygen to go to CO, well, that's here, 110.5 kilojoules. And to go from carbon monoxide and 1/2 oxygen to CO2, that's the second part, negative 283.0 kilojoules. This is a relatively simple one, and so we just have to make sure that everything cancels out and adds up. Here we have CO as a product, right? And in the bottom we have CO as a reactant. If it's on both sides of the equation, then it cancels out, and so we don't have to worry about that. We have carbon as graphite, that carries down. We have CO2, that carries down. We have a 1/2 oxygen and a 1/2 oxygen to give us a whole oxygen. And so our reaction works. Once we have that information, we add these two together, and if we do that, we add the two delta H's together. And so negative 110.5 plus negative 283.0 gives me negative 393.5 kilojoules. And that is, in fact, the answer. Okay. One more example using Hess's law that's a little bit more complicated, and then we'll be done with Chapter 6. So, here we are trying to figure out the enthalpy of formation, that's delta HF, of acetylene, C2H2. And so that's making 1 mole of acetylene, C2H2, from its elements. Carbon as graphite, plus hydrogen, which is H2 gas. Okay. Now we can go ahead and balance this equation down here. We know what that should be. I need 2 carbons, so I'm going to put a coefficient of 2 out there. We need 2 hydrogens. We've got 2 hydrogens, and so that's a balanced reaction. Easy enough. I'm looking for delta H for this reaction, yes, but delta H for this reaction is equal to the delta H of formation, because what we're doing is we're going from elements in their standard states to 1 mole of a product, in this case acetylene. But we don't know what that is. That wasn't given to us. And so we have 1 mole of graphite here in reaction A. We have 1 mole of graphite. But our overall reaction needs 2 moles of graphite. So what we're going to do is we're going to multiply this whole reaction by 2. And so then that's going to be 2 carbons and 2 O2s, give me 2 carbon dioxides. And if I multiply the reaction by 2, then I multiply the overall value by 2 as well. And that's negative 787 kilojoules per mole. Okay. All right. And so that gets me my 2 graphites. That's what I'm really interested in there. Now I need H2. I'm going to switch colors for H2 here. I have 1 mole of H2. And that's all I need. Right? And it's a product already. So for now, we're not going to touch anything with that guy. Okay. The last one, let's switch colors again. It has acetylene here, but we need acetylene not as a reactant, but as a product. And so I'm going to switch this entire reaction around. And at the same time, notice that this is 2 moles of acetylene, and I only need 1 mole of acetylene. So I'm going to switch it around, and I'm going to divide it by 2. Let me show you. I'm going to have 2 carbon dioxides. I'm going to have 1 water. That's going to go to 1 mole of acetylene, and 2.5 moles of oxygen. Again, I'm interested in the acetylene part of this. What I did was I switched it, so it's like flipping it, and I divided by 2, so that's like multiplying by negative 1/2. And so if I multiply this value, negative 2598.8, by 1/2, by negative 1/2, I end up with positive 1299.4 kilojoules per mole. Now we got to make sure that everything else cancels out. At the top I've got 2 carbon dioxide, at the bottom I've got 2 carbon dioxide. At the top it's a product, bottom a reactant, opposite sides of the equation cancel out. Here I've got 1 liquid water as a reactant, here I've got 1 liquid water as a product. Opposite sides of the equation, those cancel out. I've got 2 moles of oxygen here and a 1/2 mole of oxygen here, both as reactants. I have 2.5 moles of oxygen here as a product. Those 2.5 moles cancel both that 1/2 and that 2. Okay? And so now that I'm sure everything adds up, I'm only left with what I should have, my graphite, my hydrogen, and my acetylene. Then all I have to do is add all of the delta H's up. So we get negative 787.0 plus negative 285.8. I didn't do anything to this reaction. I didn't flip it. I didn't multiply by 2. So I just used this value for delta H. And I need to add positive 1299.4. And I end up with delta HF being positive 226.6 kilojoules per mole. Okay? That's Hess's law. They get maybe a little bit more complicated than this, but really not a whole lot more. Flipping, multiplying by a factor, dividing by a factor. This is a good example of a Hess's law kind of problem. Quick reminder that the chapter 6 material, is due Sunday at midnight, and that the quiz on chapter 6 will be open Monday at 3:30, closed Tuesday at midnight, and we have office hours Monday at 2. Bring questions if you have any. Between now and then, let me know if you have any questions. Take care.